welcome everybody. Hello, Vlad. Do you introduce yourself quickly?
Well, sure. My name is Vlad Mihalcea. First of all, thanks for joining this live webinar with Frank and I. My name is Vlad Mihalcea. A little bit about myself. I've been working on, previously, people know me for my involvement into the Hibernate project when I was working for Red Hat, and from my blog, which has the same name, which has my name. And Frank, would you like to introduce yourself as well?
Yeah, sure. So I'm developer advocate at Yugabyte. I've been working with databases for 20 years as a consultant mostly, and in many databases. And then I moved to distributed databases, and I enjoyed that so much that I'm developer advocate. So there to talk about Yugabyte and also get feedback for the product management.
That's great. Actually, and it's good for the audience because we have different backgrounds. My background is I started as a developer. You started in the database world, and then both of us ended up working as developer advocates. so, so taking that into consideration, I think we can cover the both concerns that the audience has, both the development part and the database part. All right. So, shall we start?
Yeah,
I have
I will
some.
just mention that people can ask questions on
Yes.
LinkedIn, and then we will take questions when they come. So welcome
Yes.
for any question or feedback or comment.
Yes, please do so. Let's make it as engaging as possible. Make it so that it's dynamic. And if you have questions, don't wait for 1 hour to ask something. Just ask it, and we will do our best to answer it right away. All right. So for the first part, I'm just going to start with some slides in order to introduce to you to what we want to discuss. What we want to discuss about today. The goal of this webinar that we're running today is how we can scale Spring applications. Why Spring applications? Because Spring is one of the most widely used framework for developing application if you're using Java, Spring and Spring Boot, and how we can use it to speed up and to scale the data access layer using distributed SQL in general and using YugabyteDB in particular, because that's what we're going to focus on. You will see that it's extremely easy to use it. We'll jump over the introduction part because we already done that. And right from the start, I wanted to show you something which is I would say this is very important to start with, because for many developers, not only Java developers, but many applications developers, the database is like a box. You are sending queries to it, you get the results, you get a response back from it, but it's most like a box that you don't necessarily have to think about its internals when you're working with it. And that's nice because it means that the SQL abstraction worked, and it has hidden away from you all these implementation details. So from an abstraction perspective, you can think that SQL is a success because you don't have to think about its internals. However, when it comes to performance, you really need to know about the internals, because that it's in the internals where you'll find the key to various performance problems and the solutions to them. And just a quick introduction: if you unbox the database and you take a look inside, you will see some components there, and eventually everything is going to be stored on the disk. In a database, you have tables, you have indexes, and in the end everything should reside on the disk, because if it doesn't reside on the disk and you unplug the database, you can lose data. So eventually you want all the data to be on the disk to be durable. But even if you're using the most expensive and the most advanced solid state drive, NVM memory, the disk is very slow compared to memory. It's always been very slow. Over the past 40 years, the disk has always been extremely slow when you compare it to memory. And if you always have to go to the disk to scan an index, or to seek through an index, or to find a record in a table, that would be slow. So databases, relational databases, have evolved in such a way so that you can keep, they can use the memory. And when you are requesting a page, when you want to read something from the database, the smallest unit is one page, like 8 kilobytes in Postgres. And when you load it, if it's not in memory, you load it from the disk, but then it's going to be stored in memory in this buffer pool, or you can find it under different names like shared buffers in Postgres. That's where it's going to be stored. And the next time if you go to the execution plan, you will see a logical read, which means that you loaded that page from the memory, not from the disk. So that's how these databases work. They need to use the memory to speed up the access. But the thing is that uh, this also poses some restrictions. For instance, when you want to change something, you don't change it directly to the disk. You change it on the page that it's in the buffer pool in memory, and then you commit your transaction. And you might think that when you commit the transaction, that change from memory is automatically applied and flushed to the disk. But that's not necessarily true. This synchronization is actually done asynchronously, because this buffer pool can actually be huge. This one can take like 80% of your entire memory in the database can be allocated only for the buffer pool. And synchronizing all that on every transaction commit would be impossible. So the database does it asynchronously. That's why it uses this redo log. It uses the redo log so that when you commit, it writes the modification that you've done in the redo log and flushes that, it synchronizes that to the disk. And then it just has an asynchronous process which synchronizes the in-memory state with the data on the disk. But this has some limitations, and these limitations can be seen in the typical architecture that you're using with relational database systems. Because unless you have a trivial application which can work with a single node, most of the time, if you're developing an application that has non-trivial traffic, like you have at least, it's on the internet and you have tens of thousands, maybe 100 million of users, and you have quite a lot of traffic, and you want to scale that traffic. So you're using database replication, which has two goals actually. One is scaling, because if you have more nodes, you can have more resources and you can split the traffic that can be handled by multiple nodes, not by just a single node. And the other thing is that if one node crashes, then you don't lose the all availability. You just don't become unavailable entirely. You can still serve up requests using the other nodes. So those are the primary goals of using this replication. But if you take a look, this is the most typical way of doing replication, where you have a single primary node and multiple replicas. These replicas accept read-only traffic, like read-only transaction, like reading data. But all the changes have to go to the primary node. So that's one limitation that we have here. When you're developing your Spring application, you want to scale your application. What you're going to do, you're going to use this replication. You can use something that I can show you in the code later. Have this abstract routing data source, which based on the transactional annotation, it can take a look there and see, is it read-only? I'm routing it to the read-only data source, otherwise to the primary data source for read-write transactions. But eventually, you're going to have a single primary node, which can only be scaled up. You can only scale that vertically, and that can be a limitation. And compared to that, distributed SQL database doesn't it's for instance, it embraces the fact that you have multiple nodes right from the very beginning. So it no longer relies on that memory that buffer pool that we discussed about previously about relational databases. Distributed SQL databases use the nodes implicitly, so they were designed to embrace a distributed systems in the first place. and that has many advantages. For instance, in the case of YugabyteDB, you don't have a single primary. Like, you don't have like the typical architecture that you have in relational databases where each node duplicates entirely the other node. So you have the replica duplicating everything that it has on the primary. In the case of YugabyteDB, every node can be the primary of a given shard of data and the replica of other shards of data. So these distributed databases like YugabyteDB use automatic sharding and distributed systems. Maybe Frank can can add more things about this
Yeah,
architecture.
we will try to answer the few questions that came immediately about the need to scale. For example, there is one question from Vlad Stefan. Hello, do you know you need to scale up or down the application? How do you know it is the DB that should be scaled? So yeah, that's a very good question. The first
Great.
reason to distribute is high availability, as we will see. About scaling, then that's about observability. By default, the distributed database do not provide more or less ways to know if it's the database that is the bottleneck or not. Then we have performance statistics for that. What the distributed system provides is that you can quickly react. So the big difference is that with a monolithic database, as Vlad, you mentioned just before, with a monolithic database, if you need more resources, you need to start it on a larger instance, and then you have to stop it to start it on a larger instance. With a scale-out architecture, you can just add new nodes, so you can react from that. There is also a question from Umesh. As a developer, what are the main needs to focus for scaling? I think we will answer that during
Sure.
this talk, especially high availability and elasticity.
Hmm.
There is also a question from Ziodin. What does the mean other Cassandra API? Is it Cassandra under the hood? And maybe I can explain that
Yeah, sure.
quickly on this architecture diagram. In
Hmm.
this diagram, you see YSQL, the query layer, and you see below DocDB, the distributed storage and transaction. And this is not Cassandra. It has some similarity in the fact that it is sharded and replicated, but it's different mostly because DocDB is transactional. There is nothing like eventual consistency. Everything is consistent. And in Yugabyte, there is the Postgres API, the SQL API. There is also a Cassandra-like API that is compatible with Cassandra application, but that doesn't mean that it works like Cassandra. It just provides the same API and the same scalability, but with full transactions.
Hmm.
And
And with SQL.
yeah, and there is also another question from Ali. Why and when should we move from Oracle to something like YugabyteDB? The first thing is that YugabyteDB is open source, and the problem with Oracle is the cost and the licensing. But also there is more in terms of horizontal scalability, but we will see that later.
Hmm.
And then I'll let
Exactly.
you continue, and we will check the questions a bit later.
Yeah, so thanks for explaining this a little bit. Basically, just to add up just a little bit of context. Every node in YugabyteDB basically contains both these YB masters and these T servers. These are for metadata to synchronize and to know which node are available or not, and the other ones, like Frank told, there is a query engine part, which is this YQL, and then there's the data storage part, which is that which using that DocDB, which is basically resembles more how if the audience is familiar, how my rocks uses with rocksdb, something like that, because it's it's a key value stored internal, a document stored internally that uses LSM trees. It's not using the standard uh, uh, P plus tree and relational database with buffer pools kind of updates in place that typically work in relational database. And there are many advantages to that, especially in relational in distributed SQL databases. Now, what is interesting about when you're using, and you will see, because we are going to install these YugabyteDB clusters right from the scratch. I'm going to show you how it works in Docker. And what is going to be nice about it in the example that we're running is that we're going to create right from the start a cluster with 3 nodes. So we're not doing like typically when you are developing an application with Postgres, with MySQL, you have one database installed on your operating system, or maybe you're using Docker, but usually it's one node that you have there. The same on the QI server. Maybe on the production you will have, hopefully on production you have replication, but here you will see that we can run a clustered locally. It's very easy to do it, and it's going to be a cluster that has 3 nodes. One is going to be the primary or the leader, and then we have some followers. But even the followers are going to accept read-write transactions, not just read-only transactions. And as you will see, first, although YugabyteDB actually works with anything Postgres, you can use the Postgres driver. We will connect using pgadmin to it. uh, Basically you can use everything that can work with Postgres. You can use YugabyteDB because it builds, the query engine is built on top of PostgreSQL. So it's like a fork of PostgreSQL, the query engine, not the storage engine. And however, there is one, although you can use the JDBC driver for Postgres, there is a YugabyteDB driver which gives us with some advantages, like the fact that this YugabyteDB driver, which extends the Postgres driver, allows us to load balance. So because we have this cluster of using multiple nodes, we want, when we have an application that is running, we want to automatically route our transactions to all the nodes in our cluster. Because if we
Yeah.
do that, then we are going to see that all the nodes are going to accept reads and write operations. So
I
that was
just
all the theory. Yes.
interrupt you because there were I think you just answered a question from Milos
Mhm.
asking, is there any chance we can use Postgres for local development and use Yugabyte for production without any tricks except connection information, URL, username? So yes, you just change the connection string. I would not recommend to develop on Postgres for a Yugabyte production, because there are a few things you need to be aware that it is distributed. And when you look at the execution plan, for example, you may think about the distribution of data. So basically, the compatibility helps to move an application that was developed on Postgres and moving to Yugabyte to scale out. But then I would recommend to develop on Yugabyte directly. It's open source, so you don't really need that. But the compatibility helps to move from Postgres to Yugabyte, or from Yugabyte to Postgres if for any reason you want to go back to monolithic databases.
Yes, yeah, that's a very good observation, which is basically the same. Like even if you're developing for Postgres and you do all the testing on H2, which you shouldn't, because you should test, you run your integration test on Postgres, it's pretty much the same with Yugabyte. And as you will see, it's actually very easy to install it, which is exactly what we are going to do next. Our test here is going to be just a standard Spring application. You can see the configuration here. We have the Hikari data source. I'm not using Spring Boot because I want to show exactly the components that we have. We have, you see, we even wrap the data source so that I'm going to use data source proxy for better logs. But then you have this local container entity manager factory bin. That's Spring. That's what you have. That's, for instance, if you're using Spring Boot, you get that configured automatically by Spring Boot for you. You have the JPA transaction manager, and then the typical properties there. What is interesting is here, actually, let's go back here a little bit. we are using this Yugabyte database cluster. And first I can show you that all that, yeah, we can actually do that. First, I can show you that if I'm switching to Postgres, and if I'm using this Postgres, basically, I'm just going to connect to my local Postgres database. And let's try it like that first. I can basically run this example on PostgreSQL. One second. So we can basically run this first on PostgreSQL, and then we will switch to YugabyteDB. So you can see that the same example, just switching the database, is going to work just fine, because these two databases are basically compatible. So now it's going to build the project. One second to check something first. So on Postgres, it has to, yeah, it runs on my local machine. And now it's going to start. We are going to see the database is always created from scratch. You are going, yeah, we will see here. It bootstraps the Spring application, which uses Spring Data JPA. It uses Postgres, the Postgres dialect that was picked up by Hibernate. See the inserts which go to Postgres, and everything will actually work just fine. But now we don't want to use Postgres. Let's say that now I want to do this, switch to a distributed database. So basically, I want to use this YugabyteDB cluster. But this one is going to run in Docker. And now if I'm going to my Docker, this is all the instances all the containers that I have in Docker. I have some old MariaDB, some databases here, but I don't have anything related to YugabyteDB. However, I can create all that. So for instance, I'm going to create a cluster of 3 nodes, replica 1, 2, and 3. This is going to be the first node that we're creating. I can just from the terminal here, okay, this is the first node. I can go here. You can see that it's creating it and starting it. And then I can create 2 more nodes, replica 2, replica 3. They will join this replica 1 to create a cluster, and more than that, they will use a network. So all of them can communicate uh, each other. So we're going to create these 2 more nodes. So in the end, we should have 3 nodes that are started. And not only that they are starting, you have in Yugabyte this. You have an UI that it's readily available to you. You can see the replication factor, 3 nodes. We can go to the tablet server. We can see all the nodes that have been created here. And the same test, we can now run the same test using YugabyteDB. But there is a particularity, because previously, when you're developing with Postgres, with MySQL, you are usually running on your operating system. We created these databases. Now I created it in Docker. So now if my application is running, I want to run in the same network as Docker, because I want it to these Docker machines to be available to run in the same Docker network. And in order to do that, I will have to modify this test here, and I will have to tell not run on local machine, run on this YugabyteDB network. And now we can run the same test that we had before. And this one is going to run now in Yugabyte. And yeah, actually there is, so this one is going to be a problem because it will not have the database there, but we can actually go back. But I want to show you how you can do it. That's one thing. So that's one difference that you'll be doing. So yes, in the meanwhile, let's open pgadmin. If you're using Postgres, this is a very familiar application that you may be using.
Basically, the
So that's
Postgres
another thing.
compatibility
So for instance, even if I
there
created
to use. Yeah, excuse me. I was just adding that the Postgres compatibility helps to use any tool, framework, anything that exists for Postgres.
Mm-hmm. So here we will connect. I'm going to connect to my local servers here. You see I have a YugabyteDB database, but here at first we don't have any database. That should be You see, I don't have this database created here, and it was expected. It expected to find this database. Why it was expecting it? Because if we go here, we see that it tries to connect to this database. But I've just created a cluster. It doesn't have that database. And now we only have this Postgres, which is standard with some metadata in it. And now we're going to create a database. Now, because I've been creating this before and deleting it, uh, it's a pgadmin that it will create a database. It's going to throw an exception, a warning here, comes from SQLite internally for pgadmin. They have some issue there. I should report it. But anyway, that's not important because it's not related to YugabyteDB. Now we have our database here created, and we're going to run our test. And when this one runs, we should see, if it runs correctly, we should see it logging, and then we are going to go back to this to the console to see exactly how those tablet servers are being accessed by these transactions, because all of them should be activated. I should actually accept the transactions. So we will see here what now this application is starting here. Because it's running in Docker, it's running slower because it's running in Docker. In IntelliJ IDEA has to start a Docker container, create a Docker container, start the Docker container. So of course it works slower than if I was running it myself on the operating system. So it's not the database that's running slowly. It's basically IntelliJ IDEA with this Docker machine here that it's not running as fast as if I'm doing it locally. But there's a goal why I'm running it like that, because I want to show you later how you can access the cluster there. All right, so it will now it does this bootstrapping part.
Maybe during that time I can look at the questions.
Sure.
Yeah, there is a question about how it is distributed. So question from Suresh, how the data is distributed
So
for a given table or the
so here it's
distributed
running.
nodes.
One
Yeah.
second, just to show you this part first. You can see here in the right column that it accepts all the nodes accept. So basically this answers the question. This is distributed.
Yeah.
All these three nodes now are accepting writes. So all these insert statements, because basically I'm inserting a lot of data here. There are a lot of inserts and now a lot of selects running. So if I'm going back, actually, if I'm going back here, I'm going to see that now reads are being done. So first I was having writes that were being distributing to all the nodes, and now I had the reads being distributed to all these nodes. So that's how it's distributed right from the start. Because the test, what it was actually doing, if we go back here, we can see that it had two parts. One part was a part where I was creating some in-memory 5,000 posts, and I was calling this service method, which was taking all these posts, it was splitting it into batches, and then for every batch, it was sending a batch to and running in a given transaction for and executing that using multiple threads using an executor service. And so it was using multiple threads to execute them. And then each transaction was executing in a given on a given node. So these writes, all the writes were being distributed across that cluster. And later, after we were done, and I was doing the same thing, I was doing some find by IDs using this method here. Basically, this one was also trying to find all those, and it was distributing this load across why it was distributing the load? Because each across all this cluster of nodes, some of the nodes are going to be the primary of a given for some entries, while other are going to be the primary for other entries. So data is going to be distributed. So when you want to access, YugabyteDB will figure out what is the node, the tablet server responsible, that is going to store that record and is going to route your request automatically to that. For instance, if you didn't, let's say that you developed an application, you are developing an application with Spring and you want to do something similar, and you're not using YugabyteDB, what you have to do, you have this. I have an example. Everything I'm showing you here, it's actually in this high performance Java persistence GitHub repository. So if you go to GitHub to my name, you will find it's the second repository. Every example, it's there. So if you want to do something similarly with Spring, what you can do, you have to define your read-write data source. This is your primary. And then you can define your read-only data source. And then you have to use this transaction routing data source, which based on the fact that your transaction is read only and read write, you are going to do this routing, which is done now automatically by Yugabyte. But if you're using Yugabyte, don't have to do that. And even that has some limitations, of course, because the read only, for that you have to do load balancing one way or another. So it's not that easy. And I have another example here. Actually, this one is going to be actually even more interesting, because now we're going to do something like that. We're going to insert the data, but this time, and then we're going to run for I think it's for 5 minutes. For 5 minutes, we're going to run this test, and we will try to access in this cluster. We're going to try to access some records randomly, and then what we are going to do, I'm going to go and stop one node from the cluster. So before I'm running that, when I'm running this, first of all, let me run and let me make sure that it runs. No, I'm going to stop because I want this one to run also on the YugabyteDB network. So I'm going to run it now. We will let it running. After it starts, we are going to see that the queries are going to run, and then I'm just going and stop one of the replica nodes. Now they are all running nice. I can see that all of them are running because you see running. All of them have been running since I created them. So now we're going to run it. We will go here to see that we have the read operations. Right now, if I'm doing a refresh, it's 0 because it doesn't accept any read. We are only bootstrapping our application. So right now, no one is querying the database. Now we're only bootstrapping it. When we are going to see exactly that the application was being started by IntelliJ IDEA. That's the part which takes the most in this presentation. It's IntelliJ IDEA, not the actual database part. Once it's there, it's pretty fast. And once it probably it's also because my laptop is 6 years old and I didn't do the upgrade. So yeah, I think that I can keep it for 2 or 3 more years, and then probably the demonstrations are going to be. But then what are we going to fill the 1 hour, right? The slot for the webinar. So then I'll have to come up with more examples to fill up all that time. All right. So once this one starts, we will see that first we will make sure that everything works correctly, and we have reads. You see now at first actually they are going to be the write part. It's going to do a write part, and then it's going to do those reads. We will see something like fetching. When you see fetching entity, it means that it already does what it is supposed to do. So you see we are doing these reads now, and now I'm going to the terminal and I'm going to run this command, and I'm going to stop the replica 3. So what will happen? We go here, you see replica 3 was exited, and now we go back to our log here, and we will see some exceptions here. The database, the application database will figure out that the node was down, and now it simply resumes. Everything now starts working. So it basically it did this failover automatically. And if we go back here, you will see that in the tablet server, it will basically at first it only marks the node. You see this node is unavailable, and after a minute it's going to mark it and change the state into it's going to be dead. It's not going to be alive. We will refresh it and you will see it. But the interesting part is that the application hasn't stopped. It basically worked. So think about it. How would you what exactly would you have done for your Spring application to do all this failover automatically? I didn't do anything in my code. It just worked automatically because YugabyteDB was designed to work like that. So if you're developing this kind of applications that require distributed load, distributed write, distributed reads across a cluster, I would say there's a lot of benefits to using distributed SQL instead of trying to emulate it. You see, this node is down. Actually, we can restart it. We can restart it now. And once it's restarted, it's going to be picked up automatically. At first, it's not load balanced, but then it will load balance to it. Once you see, now it's load balanced, and it can distribute traffic to it at all. So it's quite, I would say, this is very convenient the way that this application is running. The same application I could run also on Postgres, and then I could stop the service. But guess what? It's going to happen. It's not. It's just going to break at all, because if you're doing this standard replication, and if you're doing the manual switch over from one node to the other, then you'll have to, of course, once you're notified that the primary node is down, you have to promote a replica node to the new primary. Or if you're doing it automatically, then the solution is going to do that for you. So I'm going to stop this test because it runs for 5 minutes. But basically, that was the interesting part. So we stop a node, and the application figured it out. Some transactions were failed, but then the whole process went on further on until the driver discovered that the node is down. It was marking it as unavailable, and everything continued nicely. So it was just a small interruption, but then everything worked perfectly. We didn't have like an outage of 1 hour, 3 hours, 3 days until we figured out something was wrong with it. Now, to make some comparisons, if you're using Amazon Aurora, you may have something like that, and Amazon provides this to you, but there are some limitations to that as well, because you still have one primary. You may have failover, but you still have one primary, and scaling those read-write transactions will have to be done in such a way that basically then, when you cannot optimize your code and you reach your maximum capabilities of what you can optimize, then what you are going to be forced to increase the instance. So you'll have to switch from a cheaper Amazon instance to one which is more expensive, that has more resources for the entire cluster, of course, not just for the primary node. But when you will take a look at the bill, is going to be, you are going to see for yourself that this solution is going to be more expensive. So let's see. Do you think, Frank, we have more questions from the
there
audience?
is a question from Venkat. What happened to in-flight requests? So maybe I can explain quickly what
Yes.
happened. So there are different cases. The application was connected to all nodes because it takes a connection from the connection pool, and then the driver connects to the different nodes. So those that were connected to the nodes that was taken down have to reconnect. That's done automatically by the driver. The application gets an error, of course, because it's disconnected, and then it immediately reconnects. So that's for the applications that were connected to the node that fails. For the others, some of them were currently reading and writing to a shard that was in the node that fails. And there it just waits a few seconds for the new raft leader election on another node. So they don't see an error, they just wait a few seconds, the TCP/IP timeout, basically.
Mhm.
So that's what
Yes.
happened with ongoing work. So, the connected one have to reconnect, of course, and the others that were working on this node just wait to be able to continue the same work transparently on the other node.
Yes, actually, you see, when I created data source, I used this Yugabyte cluster aware data source, and then I set this connection timeout and the socket timeout so that to reduce the time it takes until it detects this kind of connection failures, communication failures to the node, and to mark it, to throw the timeouts in order to avoid to wait for a very long time. This is equivalent, like for instance, when you want to take a lock, you want to modify a record, but that record has already been modified by someone else, and they took a lock on it. And then if you're not using something like no wait, you're going to wait for as long and block for as long as the other transaction runs until they decide to commit or roll back. This is the same with this situation, because here, if we have this communication connectivity issue here, we can no longer connect to that node because that node is down. We're going to wait for maybe for 30 seconds, 1 minute, 5 minutes, and we don't want to wait for that long. We want to react probably 10 seconds. This is a little bit on the low side, because in my case, I was running only a test. But in your case, for 30 seconds, you can give like at the most 30 seconds for your node to be unresponsive. Why it can be unresponsive? For instance, I can give you some examples. If you have it, it can be because of the network, but also, for instance, if let's say that it's not a database, you want to connect to a server and that one runs on Java, a garbage collector, if the garbage collector kicks in, that would be it can make the application unresponsive for 1 second or something like that. Maybe that can happen. It's the same with the database. It can be become unresponsive for various reasons, but that doesn't mean necessarily that it was down. But if it if it's still unavailable for longer than the time that you know that it shouldn't take more than that, like 30 seconds, 1 minute, then it's you are going to get a timeout, and then you are going to react to that, connect to some other node, and that node is going to be marked as unavailable. So that's how. But that all everything that I showed you worked automatically. I didn't do anything. In fact, the same test that we were running, this read write test, if I'm changing now and running it on Postgres, it will run automatically on Postgres. It's the same thing. I am not doing any change. I'm basically, actually, no, not this. I have to change the database as well. So I'm going here and I'm going to change, tell it to run on Postgres. And now it's going to run on Postgres. You will see that it also starts right away, because we're no longer starting it in Docker. It starts on the operating system, basically in the JVM, even outside of IntelliJ IDEA. So it bootstraps quite rapidly, but then it's going to run on my local Postgres. Same code is the same. I'm not going to change anything. Why is because we are benefiting from years and years of abstractions. JDBC, which is an abstractions which allows us to connect to Postgres, to YugabyteDB, SQL, which is an abstraction. This one runs on Postgres now. You can see it in Postgres. I can actually go, what is this? It's called post, because I can go here in Postgres and refresh my tables. And I'm going to see this post, and I shall see here a lot of these posts that are created here. You see there are lots of them. All those have been created right now, and they are being fetched. So this one runs right now in Postgres. It's the same. It's basically the same thing. So it's the same. You don't have to do any change to your application, which is, I would say, this is quite advantageous. Like I was saying, we're basically our applications basically are just piling up abstractions over abstractions. If you think about it, SQL is an abstraction. It's the abstraction of the underlying data structures in the database and the algorithm to query that data. SQL is the abstraction of that. JDBC is the abstraction of the communication protocol to the database. And then we're using Hibernate, which has the JPA abstraction, which uses the Spring Data JPA, which is also an abstraction. And then you are not using that. You're using Spring, which is also an abstraction of the abstraction of the abstraction. The good part of all these abstractions is that it allows, not only that it makes your life more convenient when you're, because the whole logic, everything that I was running here, when you think about it, it's just this is the whole almost all the code that I'm running, it's encapsulated just in a few classes here. It's not even something out of the ordinary. Like the post repository is just barely some definition of it. And then I only have one entity, this configuration, a very simple service, and the test itself. But so from a convenience perspective, these abstractions provides you the benefit of not having to think about every little detail every time. But when you have performance problems, you kind of have to think about how it works. So just because you're using the abstraction doesn't mean that you don't have to understand it and know how it works, because you still have to do that, and it's important even for yourself to understand how things work, even if you don't have to do performance tuning, but especially if you're doing performance tuning. That's one thing. And the other thing is that having these abstractions allow you to grow your ecosystem. Think about it. Now, YugabyteDB chose to have this compatibility with Postgres, right? So it can benefit from anything that was previously developed for Postgres. pgadmin, we use pgadmin to create the database. But then all these applications, which can work for Postgres, can also work for Yugabyte DB with no change. Of course, there are some differences. Like for instance, by default in Yugabyte DB, you have a different isolation level. You have a snapshot isolation level, which is stronger than the read committed one in Postgres. And for this reason, you also have a different concurrency control mechanism, and you might have different exception being thrown in response to some anomalies that can happen, because more anomalies will be discarded than normally, which normally are allowed in Postgres. And so it's not like uh, you if you switch from one to the other, it's you of course it's you have to think about some corner edge cases, which probably Frank can tell you more about that part, of course.
Yeah, we had a lot of questions that I tried to answer online.
Okay, thanks.
For example, about the hash sharding, this is automatic sharding. So as you mentioned, different from application sharding. When the hash function is applied, then ranges of hash values go to tablets and they can be split. So you can start with one table into a few tablets, and when you ingest more data, it will be automatically split behind to be able to distribute it more than that. There is also a question. Yeah, a question about for you, Vlad, about the code that you demonstrated. I think you have it on GitHub.
It's here. You
Yeah,
see, if you go, this is the name, Spring Batch YugabyteDB test. You go here, and this is everything. It's everything I showed you. It's here. You see, this is the test. You go to this repository here, and you find all the classes. So it's on my name, high performance Java persistence, and if you can just search for Spring Batch YugabyteDB, just Spring Yugabyte. If you fork this and put and install it to IntelliJ IDEA, you'll find it there. So everything is it's already there, and you can test it yourself using the same thing that I already showed you.
there is also a question from Milos. Can we
Mhm.
connect with R2DBC or something async reactive instead of JDBC?
Mhm.
I think we can because it's the Postgres
Yes, you
driver.
can, of
I don't know
course.
if you tried.
I haven't tried, but yes, of course, everything that works for like the R2DBC for Postgres should work in the same way for if because that's just the API that sends the commands to Postgres, but are the same commands that are going to be sent also to YugabyteDB. So it should work just in the same way. But then that's not the problem actually. The problem is that if you're using reactive, you can no longer use everything that I showed you. You can no longer use the standard JPA, this Hibernate. You can no longer use the standard Spring Data JPA. So all this ecosystem that was built on top of JDBC, it's gone. So you have to switch to Hibernate reactive. You have to switch to a Spring reactive. So your entire stack should be reactive, and that limits your options in ways that might not be worth in the long run. Now, also think about it, why you want to go reactive. If you want to go, if you want to embrace reactive for performance and scaling, that's not the right reason. Think about it. Everything on the internet that we're using was built on top of blocking database access. Facebook, YouTube, Twitter, Pinterest, all these servers that we're accessing were built on blocking API and blocking just like JDBC, but we using other programming language drivers. But it was all blocking, and it works and it scales. So you don't really need that for scaling. Where reactive would be useful is if you have this kind of application where you need to do a lot of things in the application side, and you don't want to block on the database waiting for the database because you will need to do something else. But if your application doesn't do that, and you're not blocking on your request, what are you going to do then? What else are you going to process? Because the user waits for the things that are on the database side. And also think about it. If you optimize your application and it runs so fast that it takes a very small amount of time to block, would it matter whether it blocks or not? If your transaction response time is 5 milliseconds, does it matter so much whether it's blocking or not? What are you going to do in those 4 milliseconds there? What else? So those are very good questions that you have to think whether before you think about embracing reactive or not, whether it's worth or not for you.
Yeah, that's very interesting. Maybe we can also mention that this database is really optimized for OLTP, short transaction with high throughput. The
Mhm.
goal is not to build a data warehouse on that, because for a data
Yes,
warehouse you don't really need transactions, so you don't really need
exactly.
those distributed transactions. So I'm looking at, I don't know if you want to add something, and I'm looking at the questions.
Yeah, I can also
Uh,
take a look. I'm not sure I see the questions. Oh,
Yeah,
they're in
I'm
the.
looking at them on LinkedIn, but there are a lot.
Okay,
So I tried to catch up, and I
okay.
answered some of them online. So Milos is saying great insight on reactive, and yes. A question from Anand: how node synchronization work in YugabyteDB? Is it sync or async? What about the latency among the nodes? So basically, everything there is sync. This is why it can recover automatically without any data loss. Everything is synced. The idea is that each shard is a raft group. The raft algorithm elects a leader, and here we have replication factor 3, so we have two followers. You read and write from the leader. So this is how it is consistent, because you read and write in the same place for one row. Another row will have the leader on another node, and this is how it is distributed. But for one row, it goes to a specific tablet, and reads and writes are going to a specific leader. And when you write, it sends the write to the followers and wait for the acknowledge of the majority of them, the quorum. And
Mhm.
this is how it knows that. So the followers do not know if they have the latest change, except if they talk together. And this is what happened if the node where a leader is down. Then the two followers didn't receive the heartbeats for a few seconds, and then they decide to elect a new leader. They talk to each other, and then they know which one has the latest value, because they know that the majority of them has acknowledged the changes. So this is fully synchronous, but synchronous to a quorum. And this is how it scales. You can add more nodes. You will not have to wait for more than the one follower in case of replication factor 3.
Mhm. Thanks for the explanation.
And another question from Ziodin: even API expose should, I don't really get the question about reactive up to DB calls, but yeah. But your explanation of on React is very interesting because I get a lot of questions.
Yeah, it's a it's been a trend. Like for instance, it was like with microservices, reactive, and it was a buzz about that, and people got this impression that they have to do it because it is like a ticket for scaling, but that's not true. I mean, who sold that idea actually sold a false dream, because in reality, if you have performance issues, you just need performance tuning. We've been doing performance tuning since the very first day when we starting doing programming. This is the same old thing that we keep on doing when you're doing performance tuning, which is basically the thing of doing more with less. So basically, I'm doing a lot of stuff with the least amount of resources that I can, and that's basically the goal of performance tuning. And if you do that, you don't really need React. And I can give you some very, very concrete examples. I mean, think about it. We have performance Stack Overflow. This is a site number. It was on Alexa, it was the site number 50 in the world. 1.3 billion page views per month. And that one uses 9 web servers to serve all that traffic. But guess with what? With a single SQL Server node and only one for backup. A single node in SQL Server that has 1.5 terabytes. So why I'm telling you that? That hasn't been built using reactive programming. It was blocking. Why it works so fast? Because you can see here it can process 11,000 queries per second, and where it's 25 or something like that milliseconds, it tells you that the home page takes, so it takes 12 milliseconds to load the page. And if I remember correctly, it was taking, the response time was something like 20 milliseconds for every transaction. That's why, so if you optimize your application so that it processes data so fast, you can do it even with a single node. But if you have multiple nodes and you keep on embracing the same philosophy, you can actually scale quite nicely and basically process tons of volumes of data using uh, just standard stacks, the stack that we're having. Like for instance, I can give you another example. Shopify. You can see here Shopify Black Friday Twitter. So you can see what they've been doing on Shopify uses, that's very nice. It uses a monolith, actually. Yeah, that's not the page that we're interested in. This is from 2021. They have another one in 2022, which is even more impressive. But you can see here that for their own monolith, it can process 43 petabytes of data. And it runs on, this is Ruby on Rails on MySQL, and it processes volumes of data that you cannot even imagine this amount of data, and it's all blocking access. So for performance and scaling, you don't really need reactive for that. Reactive is for different things. It's for infinite streams of data, for data where you don't want to block because you need to do some other things, whatever. It works nicely with Node.js because they have a single node, they have a single event loop, but it's not necessarily the same in Java. If now in Java we will have uh, lightweight threads like Loom brings, and then you will have to think whether the new programming style fits better than using reactive, because it provides with more flexibility in terms of API choices.
Perfect. I think we are just in time. If you have a conclusion or...
So the conclusion is that I would say that, well, first of all, thanks everyone for participating. And as a conclusion, I would say that to wrap it up, the benefit of using distributed SQL, because this is something new. Previously, we only had SQL Server, Oracle, Postgres, MySQL. But the thing is that it's not just JavaScript frameworks that evolve, and we get more JavaScript frameworks every month. But actually, things are, of course, moving in the database world, not as fast as JavaScript and CSS frameworks, but a lot of good things are happening and they are evolving. And I would say that distributed SQL for this type of globally distributed applications where you need to scale, you need to have availability. That's a very important where you need to have availability, multiple nodes. I would say that the fact that it's being designed with distributed it's being designed with distribution in right from the start, that can be a big benefit. And as I showed you, we built it from the start. I created a clustered everything from the start. It's very easy from the developer perspective. It's not difficult to give it a try and to keep an eye on. If you have this type of application, it might be a good candidate to try to use a distributed SQL instead of just sticking to only to Postgres or MySQL. So you can give a try and in the end figure out which one provides you with the best approach for your application, because there is no recipe that works for everything. In the end, you'll have to find the technology that fits perfectly with your requirements.
Okay, yeah, perfect. In the LinkedIn chat, there is the link to the Slack channel where you can add have more questions. Thank you very much for all of those questions. And if you have more, there is the Slack channel, and you know how to reach Vlad on Twitter and his
Yes.
blog and all that.
So thanks everyone for participating. Thanks Frank for co-hosting this webinar. So we did it together. And I hope you got something useful from this, and see you in the next events that we may be running in the future.
Okay, thank you very much.
Thank
Goodbye.
you too.